backbone network generally uses a particular network protocol for packet transmission, such as IPv4, whereas non-backbone networks may use other protocols, such as IPv6 and novel IPX. If the backbone and non-backbone networks use different protocols, packets cannot be transmitted between the non-backbone networks over the backbone network. GRE addresses this issue by encapsulating packets of a protocol into packets of another protocol. This video will walk you through a practical example of how to configure GRE with dynamic routing, so that IPv6 traffic between users can be transmitted over an IPv4 GRE tunnel. In the figure, device A, device B, and device C belong to the IPv4 backbone network and run OSPF. To enable PC1 and PC2 to communicate, you need to deploy a GRE tunnel between device A and device C. Then, configure an IPv6 static route to send packets destined for the peer end to the tunnel interface. On PC1 and PC2, specify device A and device C as their default gateways, respectively. The configuration process is as follows. First, configure IP addresses for interfaces. Second, configure an IGP on the backbone network. Third, configure tunnel interfaces. Fourth, configure static routes. Step 1. Configure IP addresses for interfaces on device A, device B, and device C. Step 2. Configure an IGP OSPF in this example on device A, device B, and device C. Currently, routers support both distributed and centralized GRE. Distributed GRE uses one-dimensional tunnel interfaces, whereas centralized GRE uses three-dimensional tunnel interfaces. For distributed GRE tunnel interfaces. First, bind interfaces to GRE. A GRE tunnel can use interfaces to transmit GRE encapsulated packets only after these interfaces are bound to GRE. Second, create tunnel interfaces and enter their views. Configure the tunnel mode as GRE for these tunnel interfaces. Configure IPv6 addresses for the tunnel interfaces so that the tunnel can advertise IPv6 routes. Then, configure the source and destination addresses for each tunnel interface. Note that the tunnel source address is the IPv4 address of the interface that sends packets, and the tunnel destination address is the IPv4 address of the interface that receives packets. For centralized GRE tunnel interfaces. First, you need to configure the mapping between tunnel source interfaces and tunnel service boards on these interfaces first. Then, when tunnels whose source addresses correspond to these interfaces receive packets, they send these packets to the corresponding tunnel service boards for processing. Second, bind interfaces to GRE. Third, create tunnel interfaces and enter their views. Configure the tunnel mode as GRE for these tunnel interfaces. Note that when creating a tunnel interface, ensure that slot number specified in the target board command is the same as the X value of the X/Y/Z interface bound to the tunnel. If the two values are different, the GRE tunnel cannot be established. The command output on device A is used in this example. After tunnel interfaces are configured, tunnel interfaces are up and can ping each other. This means that the GRE tunnel has been established. Configure an IPv6 static route between device A and PC1, and between device C and PC2. Then, specify the local tunnel interface as the outbound interface of the static route, so that IPv6 traffic between PC1 and PC2 can be transmitted through the GRE tunnel. After the preceding configuration is complete, run the display IPv6 routing table command on device A. The command output shows that the outbound interface of static route 2001:db8:2:, destined for the user-side network segment of the peer end is a tunnel interface. This means that services properly recurse to the GRE tunnel. That's all for this video about how to configure GRE on NetEngine routers. Thank you for watching.